External corrosion is the second leading threat to gas transmission pipeline integrity. The Code of Federal Regulations, Title 49, Part 192, contains provisions for ensuring that buried pipelines are protected against corrosion. These criteria have worked well over the years, as evidenced by the very low rate of incidents caused by corrosion. In the early 80s, many pipeline operators began supplementing the minimum code-required corrosion control monitoring provisions with additional external corrosion testing, such as close interval survey. Additional corrosion testing methods, such as voltage gradient and attenuation survey techniques, were developed in the 80s and 90s. Since external corrosion protection of a buried pipeline is primarily dependent on a good coating as the first line of defense and cathodic protection as the second line of defense, most of the testing was designed to locate coating flaws and determine the adequacy of cathodic protection. Recently, these corrosion testing methods were integrated into a comprehensive engineering-based process called External Corrosion Direct Assessment, or ECDA. The ECDA process is comprised of 4 key steps: pre-assessment, indirect inspection, direct examination, and post-assessment. Industry experts work together to develop the process. The National Association of Corrosion Engineers, or NACE, led this charge and established RP 0502 as the recommended practice for performing ECDA. The process involves using engineering analysis, indirect and direct examination, and post-assessment evaluation and process improvement to investigate and confirm the integrity of the pipeline. In the pre-assessment step, historic and current data are collected and evaluated to determine if ECDA is feasible. Once feasibility is established, appropriate indirect inspection methods are selected and ECDA study regions are defined. Data that are researched and collected include pipe-related specifications, construction-related information, soils and environmental information, corrosion control data, and operational data. It is extremely important that all efforts are exhausted to gather all available data for the pipeline. Some companies have advanced GIS and work management systems that electronically house many of the data elements. Other companies rely on paper mapping systems, inspection reports, and maintenance records as a primary source for the data. And don't forget the ever-important field visit and interview of the people that have been primarily responsible for the maintenance and operations of the pipeline. Many times there is no replacement for first-hand field knowledge of the pipeline and its history. After feasibility is established and indirect examination methods are selected, ECDA regions are established. Regions are areas of the pipeline that are expected to have similar past corrosion histories and future corrosion conditions. Pipeline segments put into the same region can be tested and evaluated as a single study area, even though they are not physically contiguous. An example of 2 different regions could be a 50-year-old asphalt-coated line versus a 5-year-old tape-coated line in the same environment. The indirect inspection step involves performing the above-ground tests to identify the location of coating flaws or coating degradation, determine the adequacy of cathodic protection, and determine the corrosivity of the environment around the pipeline. Other information, such as pipe depth, may also be gathered if deemed appropriate. A minimum of 2 indirect inspection tools that complement one another are used over the entire ECDA region. Examples of test methods that are designed to detect coating flaws and degradation include the Pipeline Current Mapper, or PCM, the Direct Current Voltage Gradient Technique, or DCVG, and the Alternating Current Voltage Gradient Technique, or ACVG. The PCM determines the condition of the coating by looking for attenuation characteristics of an externally applied low-voltage AC signal on the pipeline. The PCM is also used to accurately mark and locate the pipeline. Both the DCVG and the ACVG techniques detect coating faults by tracking voltage gradients created by CP current and accumulating at the pipe surface at coating anomalies. To determine the level of cathodic protection, the Close Interval Pipe-to-Soil Potential Survey Technique, or CIS, is used. CIS is accomplished by measuring pipe-to-soil voltages, or potentials, at close intervals along the pipeline. On rectified systems, the testing is performed while synchronously interrupting the CP current sources. The corrosivity of the soil around the pipeline can be determined using other techniques, such as the Winner 4-pin method. To ensure that the data collected in the field can be accurately located for subsequent evaluation and potential excavation, many companies use Global Positioning Survey equipment, GPS, with sub-meter accuracy. For a pipeline that is buried in an unimproved right-of-way, the testing can be relatively easy to accomplish. However, growth has closed in on our pipelines, and testing pipelines that are located in city streets is more complicated. For example, performing CIS in city streets may require traffic control and drilling small holes in the pavement to establish soil contact. Local public agencies have comprehensive permitting requirements for this kind of work. Once the data is collected, potential deficiencies are classified as either a severe, moderate, or minor indication of a condition. The data is then integrated together with all the data collected, and priorities are established for direct examination. Indications are prioritized as either immediate, scheduled, or monitored. Immediate indications represent conditions where corrosion may be present. All immediate indications require direct examination. Scheduled indications are of lesser concern, however, could still represent conditions where corrosion may be present or may occur at some point in the future. As a minimum, one scheduled indication must be directly examined. Monitored indications are those that have the lowest likelihood of experiencing corrosion activity and are monitored for review during future assessments. The direct examination step involves performing the prescribed amount of direct examinations of the pipeline, documenting the condition of the coating and the pipe steel, performing any required remaining strength calculations, making any necessary repairs to the coating or the pipe, and performing a root cause analysis of the findings. Once this step is completed, the initial prioritization of the indications can be adjusted appropriately, and all actions required to complete the verification of the pipeline integrity can be established. When directly examining the pipe, a comprehensive evaluation of the as-found conditions is performed. There are many test methods that can be used to assist in the examination, depending on the level of coating quality and pipe integrity found. Here are some examples of the tests that can be performed: soil analysis, resistivity, and soil pH testing, pH testing of any liquid underneath the coating, complete coating characterization, including using a high-voltage coating flaw detector and testing the coating thickness and adhesion strength, performing pipe-to-soil potential reads at the pipe depth, analyzing any corrosion products found, including testing for microbiological influence, testing the pipe using magnetic particle testing, ultrasonic testing, and possibly even radiographic testing. If corrosion is found, detailed maps of the corroded area are made to assist in remaining strength calculations. Once all the as-found data are collected and evaluated, the results are combined with other pre-assessment and indirect inspection data to help the engineer understand the root cause of any conditions or integrity concerns that are present. The root cause analysis helps to solidify the past conditions the pipeline has been exposed to, its present condition, and what needs to be done to ensure its integrity for the future. The post-assessment step involves analyses of all the data collected from the previous 3 steps to assess the effectiveness of the ECDA process and determine reassessment intervals. This important step involves putting 2 and 2 together and seeing if it truly equals 4. It's the step in the process that sanity checks everything gathered, postulated, and found, and from a critical perspective, establishes the next direction to be taken for the pipeline under study. ECDA has grown from its roots of informally applying technically sound inspection practices to find corrosion on the pipeline to a mature, formal, and comprehensive integrity verification process. The ECDA process will no doubt change and improve as new techniques for data gathering, analysis, and testing emerge. The pipeline's history, current condition, and assessed future condition are all used to accomplish the very important task of ensuring the integrity of the pipeline so that we can ensure the safety of everything and everyone around it.